Hello everyone, how's it going? My name is Dan the Tutor, on a mission to become the world's greatest tutor. In today's video, we're doing a very famous optimization problem in Calc 1. It's the problem where you have this box, or really piece of cardboard, and you are going to cut off X inches on each of the four corners, and then you are going to fold up the sides of the cardboard in order to make it into a box with an open top. Now, many of my students can't visualize this for whatever reason, so I took it upon myself to actually get an 8-inch by 3-inch piece of paper. I'm going to be showing you what this looks like really quick. Okay, so first of all, I'm just choosing a random amount of paper to take off each corner. So this is not going to be the maximum volume, which is what the question's asking for. We need to choose X to maximize the volume of my new box. But that's okay, this is just for demonstration purposes anyway. Okay, so this is how much I took off on each side, as you can see. And now I'm just going to fold in on all four sides. Oh, that long one's going to be tricky. Okay, that's pretty good. And maybe now you can see what I'm talking about, Alex, when I say fold the sides in to make a box. Okay, and then see that kind of looks like a little box with an open top. And so now the question is, how much do I need to cut off on the sides of each box in order to maximize the volume when I do fold it in? So normally when I solve optimization problems, I'm trying to find an objective and a constraint equation, because that's what we always do, right? Now the objective is the thing I'm trying to maximize or minimize. In this case, I'm trying to maximize volume being length times width times height of my box. Here's length, here's width, here's height. And so that means volume, objective, equals length 8 times width 3 times height, which is the X. That's how much I'm folding in. And this is what 98% of students say, and 98% of students are wrong. And that's what makes this question especially difficult. Let me explain why. The length is not 8 and the width is not 3. And the reason why is, remember, this here in blue is really my length, and this here in red is really my width, because that's the bottom of the box, basically. Maybe I'll color code it here and you can actually see it. So in other words, the length is really 8 minus 2x, because you're taking off x on both sides. So the length is 8 minus 2x, the width is 3 minus 2x, and then the height is actually still just x. That didn't change. And so therefore my objective, my volume, is quantity 8 minus 2x times 3 minus 2x times x. And again, that's because it's the length times the width times the height. I'll reduce this later. Now the constraint. What would the constraint be? Well, the constraint is always the random number, but I don't have a random number. Like, I didn't say the surface area had to be this or the volume had to be that. So it seems like there's no constraint here, and that is true. And the reason why, and this is again a famous example, it's the only one that doesn't have a constraint, is because why was the constraint there in the first place? Normally the constraint's there because I have something like 100 equals 2x plus 2y, and then I solve for either x or y, and that gets me the other variable. In other words, I have a constraint when I have two variables. But I don't have two variables, I just have one, I just have x. So in other words, no need for a constraint, just the objective. And now I just have to start simplifying, taking the derivative, and all that stuff we do for all the other optimization problems. So to do that, I'm first going to FOIL these two. It's going to be 8 times 3, 24. Minus 8 times negative 2x, 16x. Negative 2x times 3 is minus 6x. And negative 2x times negative 2x is plus 4x squared. All of this still needs to be multiplied by x, but that's not too bad. It's going to be volume equals 24x. Negative 16x and negative 6x combine to make negative 22x, which, when multiplied by that x right there, is going to be negative 22x squared plus 4x cubed. Let me just rewrite this in the proper order. 4x cubed minus 22x squared plus 24x. That's better. And now to continue with all optimization problems, it's finding critical points, finding relative extrema using the first derivative test, and testing the points on a number line. So first derivative, that's going to be 12x squared minus 44x plus 24. We need to set this equal to 0. Now, if I did this right, and I think I did, there's only a few numbers that work really well for this problem. And I think I chose the right numbers, 8 inches by 3 inches. But we'll see. So first I'm going to factor out a 4, because all of this is divisible by 4, leaving me with 3x squared minus 11x plus 8 equals 0. And yep, it looks like I chose the magic numbers. It's going to be 3x minus 8 times x minus 1 for the factoring. If you're not good at factoring, well then, too bad. I'm assuming you know how to factor at this point. This is calculus after all. But now to actually solve, it's going to be 3x minus 8 equals 0 and x minus 1 equals 0. So x is going to be 8/3 and positive 1. Now this is the other thing that makes this problem so fun. Normally I just have one answer for the critical points, and that's going to be my maximum and minimum. But this one, it is actually really necessary that I plug these numbers in on a number line. Now here's 1, here's 8/3, which is about 2.6 repeating. And I have to plug this in my derivative, which was the 12x squared minus 44x plus 24. Or you can use the version when we factored out the 4, that's okay too. And so now I just have to plug in points in each of my 3 regions. I'll plug in 0 first, even though technically 0 doesn't work because, we can't let x equal 0. I can still plug it in to test the critical points and first derivative test. So when I plug in 0 for x, it's really easy. I'm just going to get 24, which is a positive number. Now I'll test 2, which is in between these two. 12 times 2 squared minus 44 times 2 plus 24. That's going to be 12 times 4, 48, minus 44 times 2, 88, plus 24. That's going to end up being a negative number. And then I just have to test a point greater than 8/3. Let's test 5 or something. 12 times 5 squared minus 44 times 5 plus 24. 5 squared is 25. 25 times 12 is 300 minus 220 plus 24. And this one's definitely going to be a positive result. Okay, so it looks like 1 is our relative max and 8/3 is our min, which is bad. I don't want the min, I wanted the max area of this box. So x equals 1 is going to be the answer. But one more thing I just want to point out real quick. 8/3, which remember, that's 2.6 repeating, could not have worked at all for this problem. Why not? Well, if I draw the original problem again, I think you'll see a problem if I take off 2.6 inches on either side of the box. That's more than 3 inches, right? As a matter of fact, I could only take a maximum of 1.5 inches off anyway. So really, when I was doing my number line test, you're allowed to do this. The bounds of your number line test are 0 at the low end, 1.5 at the upper end, and you only have to test positive 1. Positive 1 ended up being the relative max anyway, so it doesn't matter. But that's a cool side note, I guess. So since x equals 1, and we wanted the dimensions, length, width, and height, length is going to be 8 minus 2x, width is going to be 3 minus 2x, and the height is just going to be x. So length is 6 inches, width is 1 inch, and height is 1 inch. And that is the dimensions of my box for the maximum volume. And so that's going to do it for this video. If you have any questions, please write them in the comments. Have a great rest of your day, and I'll see you in the next video. Take care, and bye-bye.